Hi, everyone, and welcome to online lecture 24. This is ANOVA part 2. So if you recall, the last time we were talking about ANOVA, we were talking about how you could tell if it was significant or not, right? But we already had talked about the idea that just because you have a significant result, you may not know which groups are different from each other, because if you have even 3 groups, there's multiple possibilities there. So a significant ANOVA tells you that there's a difference somewhere between the groups, but not where. To figure out where, we need a post hoc or follow-up test to figure out which groups are different from each other. And that's what we're going to spend some time on next, is looking at post hoc tests, at least one particular post hoc test, and seeing how it informs us. Okay. Specifically, we're going to look at the Tukey's honestly significant difference test, or Tukey HSD. And this gives the ability to compare differences among group means. Now, you might be thinking, wow, honestly significant difference test, that's kind of a weird name. Where does that come from? And if you are curious, or even if you're not, I guess, I'll tell you that there's a lot of competition amongst these different post hoc tests, and Tukey wanted to show that his was the honestly significant difference test, so he named it as such. Okay. So in this scenario, we're going to talk about fear of spiders. That's going to be our example. And basically what they did is they took a group of people who were afraid of spiders, okay, and they put them in different groups to show which kind of treatment might be most helpful. So one group got no treatment, one group got hypnosis, and one group got systematic desensitization. And if you're not familiar with systematic desensitization, it's basically gradually exposing someone to the feared stimulus, such as a spider. Okay, so anyhow, we have our ANOVA here. We have our between groups, our within groups, our total. And we look over here and we see this is clearly significant. Our P is less than our alpha of 0.05. So we are in good shape. But where's the difference between hypnosis and none, between hypnosis and systematic? We don't know. So we're going to look at Tukey's honestly significance difference tests to figure out where the differences are. Okay. So the way to look at this test is I want you to focus on each of these lines being a row that's doing a comparison. In the first row, we're comparing none to systematic desensitization. And we see that the mean difference is here, the standard error, and perhaps most importantly, the sig value. Okay, so systematic desensitization is different from none. Great. This p-value is significant, it's less than 0.05. Now, we're going to pretend this word none is written again right here, and we're going to compare none to hypnosis. None to hypnosis. So we go across again, and we see the sig value this time is 0.659. That's not significant. That is not less than 0.05, not even close. So apparently there was no difference between the none group and the hypnosis group. Okay. Next, we see systematic desensitization and none. And you might be wondering, well, didn't I just look at none and systematic desensitization in the top row? And I would say, yes, you did, in fact. This is a repeat. You can ignore this, and you can even see that the mean differences is pretty much the same except for the sign, as is the standard error, as is the p-value. So it's really offering nothing new and interesting. So I would ignore row 3. Let's move on to row 4. Systematic desensitization and hypnosis. Okay, that's new. I haven't looked at that yet. And we see again a sig value that is less than 0.05. This is 0.025. So our sig value is less than our alpha, and this is a significant difference. Now, when we move on to row 5, we see hypnosis and none. Well, that sounds familiar too, because we looked at none and hypnosis in row 2. We can ignore that. And finally, in row 6, we see hypnosis and systematic desensitization. Well, here we just looked at systematic desensitization and hypnosis. That's the same thing. Nothing new, no new information here. So to summarize, if you are looking at one of these tables, and if you have 3 comparisons, you can just look at rows 1, 2, and 4, and you can ignore the rest. Okay, so again, that's row 1, row 2, and row 4, and ignore the rest. Okay. All right. So that's how you actually work through this kind of table. Now you might be wondering, okay, I know which ones are different, so which one's better? Which one's actually better? And there's a clue right in this table, but I would tell you as a general rule, you'll probably see the descriptives, and the descriptives would tell you the actual means, and then you could know which one it is. But if you were curious, we're looking at number of symptoms that remain after the treatment. And if we subtract none minus systematic, we get a positive number, which means there's a lot more symptoms left in the none group than in the systematic desensitization group. The systematic desensitization group, however, minus hypnosis, we get a negative number, which means that the opposite's true, right? In this case, hypnosis had more symptoms left than systematic. That's how we got that negative number, because systematic minus hypnosis gave us a negative value. If you like that, if that's interesting, great. If you don't worry about it. You'll have descriptives to look at, which will tell you the means, and then you can simply compare the means. Okay. So again, this table is just about telling you which differences are significant. Which differences are significant. In our case, we had 2 significant differences between none and systematic, and between systematic and hypnosis. All right. So now let's go through our rules. If the manually calculated, and it says F, T, or Z, but let's just focus on F for right now. If that manually calculated F was more extreme than a tabled value, which we're not really looking at, but I'd like you to understand this piece, then it's going to be statistically significant and we'll reject the null. If a manually calculated F score is not more extreme than the table value, it's not statistically significant and we do not reject the null. So here's my point. F, T, Z, they all work the same way when it comes to interpretation. The only difference is with ANOVA, we don't have to worry about that one-tailed thing, at least not in this class. It's always going to be two-tailed. So we will know that statistically significant and rejecting the null are going to go hand in hand. Not statistically significant and not rejecting the null are going to go hand in hand. Now let's get to SPSS, and this is the one we have been looking at, so this is more relevant. If the observed p-value in SPSS is less than alpha, it's statistically significant and will reject the null. If the observed p-value in SPSS is not less than alpha, it's not statistically significant and we do not reject the null. So again, I know I'm just saying this for F, but this is true for T and Z as well, right? We always want our p to be less than our alpha. Okay. Okay, so this actually is a little hard to read, but it says mind blown because I have something interesting to share with you. Now, I have been telling you that there is a strong relationship between the F ANOVA and the t-test. And it is true that for 2 independent samples, either a t-test for independent samples or a one-way ANOVA can be used, and it will always result in the same decision. In fact, F would equal t squared. So if you took your t value, you squared it, you would get F. Okay. Okay, so that's all I'm going to say about the one-way ANOVA. And now I want to talk to you about two extensions of ANOVA. And we're not going to worry too much about looking at output for these as much. I mean, we'll look at a little, but it's more about understanding what these tests are about. Okay, so the first one we'll look at is the repeated measures, which is very comparable to the t-test for dependent samples. It uses a repeated measures design. And then we'll look at the factorial ANOVA, which is used when you have more than one independent variable or factor. This is the only test we will talk about in this whole course where it can have more than one independent variable. So let's look at our repeated measures ANOVA. Now, if you recall, our one-way ANOVA is very, very similar to our t-test for independent samples. The only difference is that this number of groups goes from 2 to 3 or more. Remember, we can compare not only psychology and math majors, but psychology, math, and physics majors. And if you like, you can throw in sociology and theater majors as well, too. The t-test for dependent samples, in a very similar way, is very similar to repeated measures ANOVA. Except now, the number of values or scores per participant goes from 2 to 3 or more. So before I was going to check heart rate at the beginning of the semester and the end of the semester. Now I can check heart rate at the beginning of the semester, the middle of the semester, and the end of the semester. Okay. Or blood pressure if you like. But either way, I can do it 3 or more times for the same participants. Okay. Now, repeated measures ANOVA is calculated similarly to the one-way ANOVA. However, since the participants are in each condition, individual differences or error can be removed from the denominator, or SS within and MS within, which bottom line means we have more ability to detect differences due to the IV. So let's see how this would look. Okay. So in this study, participants were tested on their performance in a driving simulator. The higher their score, the better their performance. The participants were broken into 3 groups, where one group had no phone, a second group had a handheld phone, and a third group had a hands-free phone. Assuming an alpha of 0.01, is there any difference between the groups? So this is the data for performance in the driving simulator for people with no phone, handheld phone, and hands-free phone. Okay. Now, here's the part I actually want you to look at. Look at this ANOVA table. We have a very strong F, 11.2503, P is less than 0.01. And I want you to look at these within numbers, particularly the 16 and the 1.3333. This is the part that if I ran this study as a repeated measures instead, would go way down. In fact, I did this. I said, let's pretend that the same people who first went into the simulator with no phone, then went into the simulator with a hands-free phone, and finally went into the simulator a third time with a handheld phone. Now, you might argue with me and say, well, that's kind of a crappy study because they're getting more practice each time in the simulator. And there are ways to deal with that, which you'll talk about more in research methods if you take that going forward. But for now, I just want you to focus on this 16 and this 1.3333. Look what happened. It went down to 4.6667 and 0.5833, which means the F, because these didn't change, I'll show you that. See, 3215 didn't change, 3215, which means your F is going to get a lot bigger. It went from 11.25 to 21.72 with a P less than 0.001. So even a lower p-value, right? Before we had p less than 0.01, now it's p less than 0.001. So that main idea is that repeated measures will reduce error in an ANOVA, okay? All right. Now let's talk about our factorial ANOVA. And that's the last ANOVA we're going to talk about. So remember, I already told you what's going to change here. It's not the population mean or variance. It's not the number of values. It's not even the number of groups, really. It's the number of independent variables. So let's look at it. Right? Number of groups, 2 or more per IV, which makes sense. If you're going to have a group, you got to have at least 2 groups to compare something. But this is the key factor. The fact that you now have 2 or more independent variables or factors. Okay. So now, as opposed to just looking at whether vitamin or vegemin makes the difference in energy levels, we can also look at gender, for example. We can see if maybe vitamin or vegemin actually increases energy levels in females, but decreases energy levels in males. So we can look at more interesting questions with this factorial ANOVA. Okay. Now, the main thing I'm going to focus on with this factorial ANOVA is the power of interactions. Sometimes one variable isn't enough to capture what's going on. Sometimes the role of one variable may differ depending on the value of another variable, and that's called an interaction. So when we just were talking about, just a moment ago, we were talking about the effect of vitamin or vegemin on energy levels. And if I asked you, now knowing what you know about gender, at least for males and females, if I asked you, okay, so what's the effect of vitamin or vegemin on energy levels? You would say, it depends. Because for females, it increases, but for males, it decreases. Okay. So let's look at this particular example. Let's work through this a little bit in understanding a little bit more about factorial designs. Okay, so what we've got here is we're going to look at a driving simulator again. We're going to see how well people do in the driving simulator under different conditions. So we're going to look at sleep deprivation and caffeine consumption as our 2 independent variables. So we're going to have some people who are not deprived of sleep, and there's 3 groups of those. Some people who are deprived of sleep, and there's 3 groups of those. And in our first not deprived group, in our first not deprived and deprived group, we have low caffeine use. In our second, we have medium caffeine use. And in our third, we have high caffeine use. So at the end of the day, we have 6 different groups. Okay. So if we assume that there were 60 people total in the study, we'd have 10 here, 10 here, 10 here, 10 here, 10 here, 10 here, right? Okay. Now, in understanding factorial designs, we have to understand the difference between main effect and interaction effect. The main effect is the influence of each independent variable on the dependent variable. And there's one main effect for each independent variable in a study. So for example, in our example that we're working through, I'm just going to page back for 1 second. Sleep deprivation has a main effect, not deprived or deprived. Caffeine consumption has a main effect, low, medium, high. Now the interaction effect is the joint or interactive effect of two or more independent variables on the DV. It's when the effect of one independent variable depends on another. And graphically, an interaction yields non-parallel lines. So to understand this a little more, because we talked about an interaction effect, the dependency, but to understand a little more, let's look at some real data. We're going to look at some means, okay? So here are the means for our 6 groups. Remember, our dependent variable is driving performance. The main effect of sleep deprivation. So to understand that, we're going to look at these averages all the way over here. Here's our not deprived group, and on average, they made 5.4 correct maneuvers. Here's our deprived group. On an average, they made 4.4 correct maneuvers. So it seems, without doing any analysis or doing anything fancy here, it seems that the not deprived group may have made more correct maneuvers, right? They did make more correct maneuvers. We just don't know if it's significant. Now let's look at the main effect of caffeine. Now we have 3 groups. Low group, 2.2. Medium group, 7.3. High group, 5.3. So the medium caffeine group is the clear winner here, right? Most correct maneuvers with medium caffeine. Okay. So we could stop there, but that wouldn't tell us the whole story. So let's look a little further. If we actually draw out the line graphs, we see that there is an interaction effect between sleep deprivation and caffeine consumption. So let's understand this a little more. The solid line is for our not deprived group, not deprived sleep group, right? And our dashed line is for our sleep deprived group. So let's first by understanding what's going on with our not deprived group. Well, low caffeine, high caffeine, neither one's too great. If you really want to be a winner with no sleep deprivation, you should get medium level of caffeine. But that's not the whole story, is it? Because that doesn't tell us what's going on with our deprived group. If you're sleep deprived, it looks like the more caffeine you get, the better off you are. Even so, the sleep deprived group still doesn't do as well as the non-sleep deprived group with a medium amount of caffeine. Nonetheless, we can't answer a straightforward question. If I asked you, okay, so what's the effect of caffeine on driving performance? You would have to say, look, it depends. It depends on sleep deprivation. If you're not sleep deprived, medium amount of caffeine. If you are sleep deprived, get as much caffeine as you can. Okay. Or at least get a high amount of caffeine. Let's put it that way. Okay. So one more thing I want to talk to you about with this notation, factorial design notation. The number of numbers refers to the number of independent variables. So since here we have 2 numbers, we have 2 independent variables. Now each number indicates the number of levels for each IV. So IV1 has 2 levels, IV2 has 2 levels. This would be just like when we were talking about looking at vitamin and regimen, yes or no, and gender, male and female. That would mean that we had 2 independent variables. The first one had 2 levels, the second one had 2 levels. Whereas this one, this 2 by 3 design, once again, we have 2 numbers, so 2 independent variables. The first one, 2 levels, well, that's kind of like our sleep that we just had, not deprived and deprived. And the second number is 3. That's just like our caffeine, low, medium, high. So the study we just looked at with sleep deprivation and caffeine consumption on driving is a 2 by 3 design. Now let's, for fun, say we added in one more variable there, and let's say that variable was eye color. And eye color had 3 levels as well. Then this would be by 3. It would be 2 by 3 by 3, because we would have 3 variables. 1 sleep deprivation, 1 caffeine, and 1 eye color. Okay. Please go now and take quiz 9. The password is 2702. There are 2 multiple choice questions for you to answer. Okay, that's all I have for you for today. Stay well and take care, and I will talk to you next time.